Hi everyone, thank you so much. Welcome to week 1. In this week, we'll do 3 things. First, describe the history and phases of data analysis. Second, we'll outline the basic theory. And last, we'll explain what data mining is. Thank you so much for your time and attention. Looking forward to talking soon. Welcome again, GBA 605 Business Data Analysis and Modeling. This is week 1. We'll be covering statistics and data mining basics. The learning objectives again are threefold. First, to describe the history and phases of data analysis and modeling, create an outline of the basic theory, and then explain what data mining is. So as you know, statistics basically has 2 main schools of thought. One is originated by Thomas Bayes, and the other Sir Ronald Fisher. So in Bayesian statistics, it looks at the probability of an event's occurrence is equal to the probability of its past occurrence times the likelihood of its occurrence in the future. This is used heavily in science where instrumentation captures different measurements over time. So you hear a lot about Bayesian statistics in the lab where experimentation is done, in weather, and other places, again, where natural science occurs. Classical statistics, again, originated from Fisher, says that data fits into a known distribution. And when we talk about known distribution, this is what we all studied in statistics: normal distribution, logistic distribution, Poisson, etc. It says that all data fits a pattern. This is very important to understand this in terms of how statistics fits into management and decision support. We'll come back to this, but both of these schools of science are very relevant to the study of data analysis and statistics and data modeling. Important to this study is the fact that there's 2 main views of reality. Of course, in your real life, you probably, there are other points of view, but in this area, the 2 main points of view originate from Aristotle and Plato. Aristotle believed that only things that can be observed, that would be measured, by sight, touch, hearing, etc., were reality. In other words, tangible reality. The other school of thought was originated by his student Plato, who believed that the only important things in human existence were beyond what the eye could see, the hand could touch, etc. The only thing that lasted was an idea. So it's looking at a more ambiguous concept than Aristotle. It's much more unlimited, if you will, than Aristotle's view. In the history of statistics and data mining, there are 3 recent generations that are important. Again, the rise of modern statistical analysis emerges from the Fisherian view that says that there are patterns that can be modeled. So, as we talked about earlier, logistical, Poisson, etc., there's a logit model, which is logistical regression, probit model, which is Poisson regression, and a generalized linear model. Out of that comes machine learning methods, the 3rd generation, which really came from the artificial intelligence community using artificial neural networks and decision trees. And then out of that is the current era, which is statistical learning theory, the 4th generation, and it really talks about complex functions or kernels replacing an inner product. It says when you map data onto these complex kernel spaces, the range of possible solutions increases significantly. Again, with the complexity of the big data today, the complexity of the reality that's being scientifically analyzed and decisions are being made about, whether it's in the business world or in science, calls for a more complex and far-reaching set of tools. And that's where statistical learning theory comes from. What the scientific method is. And any discipline, any science is always based on the scientific method. So let's look at the steps. The scientific method process steps are ninefold. First, identify the problem. And in case of a business, it could be, poor results in the sales area or marketing or profitability from the financial discipline. Second, so you gather that information. The third is to form one or more hypotheses. So you might say a hypothesis might be, as we increase spending for marketing, sales also increases. So that assumes that there's a positive correlation between marketing spending and sales results. Next, you would collect experimental data. So you would collect marketing expense data, and you would also collect sales results data, making sure that you baseline the two for the same time periods, the same quarters, the same year, the same months, side by side. And then you would conduct an analysis in step 5, for example, a correlation analysis, to see if indeed there is a positive correlation between marketing costs and sales generated. You'll interpret the results, which means you'll look at the correlation value. Correlation of 1 says there's perfect alignment between the two phenomena. In business, we never talk about a causal relationship because one thing cannot be proven to cause another. There's too many variables and it's too complex to say that. In science, in the lab, you can prove a causal relationship because everything is controlled. You can say as you add oxygen to hydrogen, the resulting mixture is something else, directly related to the two components being increased. So in the business world, we tend to look at correlation, obviously, in values much less than 1. Anything, let's say, 62% correlation through, let's say, 90% would say you could draw the conclusion that there is a positive correlation between, let's say, marketing expenditure and sales results. So the ongoing steps in the scientific method, and again, in all analysis, we're always trying to refine both the hypotheses and the analysis, and so that would be what goes on in steps 8 and 9, is to create new hypotheses or more refined, more specific hypotheses, and then continue to test. Evolution of the sciences, we talked a little bit about Aristotle and Plato. Before 1600, the empirical science emerged. Empirical science meant things that you can measure and quantify. That emerged out of a very ambiguous era where things were based on myths and legends and supposition without any quantitative proof. And so the empirical science era was a major step forward in scientific pursuits because, again, it was based on numbers and facts and measurements and those kinds of things. Out of that era comes a very long one, the 1600s through the 1950s, where we talk about theoretical science. And theoretical science says, a level above hypotheses are theories, and theories are a generalized view or idea about how things work. And out of theories, we then postulate certain hypotheses, and then we test them with actual data. So, theoretical science, in other words, what are the theories that can be, brought forward, and then we go in and we do experiments to prove or disprove, components of that theory. We have a better idea about how things work. And many of those theories have a name, like Keynesian economics is a theoretical framework, and a lot of research has been done looking at economic data over time. In the 1950s and 1990s is computational science, and you can see from the prefix of compute, it's all based on computers and the amazing power that computers have evolved to have over time. Moore's law, computing power doubling every 18 months over that long period of time. You can imagine, actually the reality is that computers are so fast at computing things, and that we're able to quickly do statistical analysis and other computations with ease with the new applications and computers. Then 1990s through now is the emergence of data science. And the big thing there is that we're talking about an amazingly huge amount of data that could be stored in a large repository or out on the web or other means using tools like Hadoop. And we'll get into more in depth in those things over the course. But data science is using applied math and all kinds of techniques to be able to analyze and then interpret data that's in multiple forms across geographies that were unheard of before. So this is a new era, and it's a very exciting time. Big data is a result that's come about in that technology. In the 1960s, the computers were very primitive compared to today, but a lot of data was collected, at least relative to that time period. But you needed very complex programs like Fortran or COBOL with very specific instructions to be able to analyze that data, because it was stored in a very primitive way, in a very proprietary way, I should say, based on the different kinds of computers that existed. In the 1960s, the relational data model emerged. Companies like Oracle and others, were able to not require such sophisticated computer programming, but in the database itself, the database management system was able to answer very specific queries that were not computer programmed, but more database programmed in nature, and were able to analyze data. And then in the 1980s, the full-blown relational database management system, very complicated data models, concepts and applications such as object-oriented design were able to make things more of a business or scientific in nature. For example, object-oriented design allowed things like object-oriented programming, which we would have to identify certain characteristics or attributes of a business nature. For example, in an automotive company, an object-oriented design in a relational database might include an entity which is defined enterprise-wide called automobile. And the automobile may have its requisite components, the wheels, the transmission, and those things as characteristics, as well as the owner, who owns it, what kinds of warranties are associated. Each of those things would be considered an object and could have an enterprise-wide, what they call metadata definition, that all systems that integrated with each other can use to be able to ask questions across many, many different platforms. In the 1990s, as the emergence of data mining, data warehousing, you hear the terms like business intelligence and those kinds of things, those were the vogue. And then in the current time, the 2000s, stream data management and mining and large web technology applications such as XML allow for global information systems. I did a project for General Motors, and basically it was a sales support system based on a package called Siebel, and there was a single system implemented in Detroit, but it was accessed and used by clients, automotive companies all over the world. And this was not possible until after 2005, for example. Another word for it is knowledge discovery from data. So when we talk about extraction of data, we're trying to find meaningful patterns of knowledge from a large amount of data. In other words, as an executive in a company, you know that you have a lot of data out there, a lot of systems, a lot of things that you're paying a lot of money for. But the question is, how do you make that data useful to you? If you want to know what kinds of profitability, what is the profitability for your entire enterprise, that would be a data mining or maybe a dashboard or something like that that would give you that answer in literally seconds. Alternative names, again, is knowledge discovery, databases, and business intelligence, again, is kind of are other names for data mining. So why do we use data mining? Why is it more important now than ever? And the main reason is the amazing growth of data. It's everywhere. every smartphone, every lab piece of equipment, every database system, everywhere there's data. And it's all very centered on certain functions, such as either the scientific lab or business or even government policy has a lot of data. But the amount of data every year is now more than the amount of data created the previous year back to the history of mankind. So it's growing exponentially every year. And so, one concept would have us all, being crushed by the amount of data that's out there. Another concept would say that because of data mining, we're able to interrogate and have very relevant interrogations of data and very meaningful information that we couldn't have before. Let me give you an example. When LeBron James came out with his new Nike tennis shoe, Nike was able to use Twitter to find out what the sentiment was. What was the consumer perspective of the new shoe? LeBron James obviously is nothing compared to the Michael Jordan, right? So the new Michael Jordan tennis shoe comes out, there's all kinds of positive feedback on that. So while we're data rich, we're information poor. In other words, there's so much data, the amount of actual knowledge that comes out of it is absolutely minuscule. And so this whole field of data science and using data mining tools, the need for people that understand that is growing more and more every day. Is marketing, being able to figure out what the market is, who are the customers that you have, who are those customers that you don't have but would like to have. Customer relationship management looks at customers that you already have and how can you keep them. It costs 5 times more to attract a new customer as it does to keep a current one. Looking at risk analysis, in other words, there's data out there from past fraud that can be analyzed to try and prevent future fraud. There's also data about customer retention. What kinds of customers are you retaining? Why? You can actually look at surveys or create new surveys to find out what people like or dislike about your product. There's so many applications out there. We mentioned scientific pursuits. Bioinformatics is part of biological research, and it's helping to streamline not just data discovery but the whole data driven discovery of new drug products and even the approval process through the FDA. So this slide highlights some key steps. We've talked about them. Having clean data is very important. Having access to all the relevant data from even multiple data sources is extremely important. Selecting the data that's relevant to purpose. Transforming data that may be stored in multiple forms, within multiple repositories, multiple systems, multiple applications, even geographies, using Hadoop, and then mining that to, asking the relevant questions to see what kinds of patterns may exist in the data, and then presenting or visualizing that data in a meaningful way that even a non-technical person can say, I get it. This graphic is just showing the process steps, if you will, cleaning, data warehouse, task relevant data, then mining that data, and then looking for a pattern evaluation. Data mining or data analysis and data modeling is actually a convergence of multiple disciplines. It's not just one thing. It obviously takes advantage of database technology, statistics, machine learning, visualization, information science. So many different disciplines are involved, and the tools take advantage of all of them to create effective decision support tools for management to run their businesses better. Thank you so much for your time. Looking forward to week 2.